Hello everyone, welcome to Knowledge Hub by Sri Chaitanya. This is Shravan Kumar, Senior Chemistry Faculty. So, in this session we are discussing about the Faraday's laws. So, this is the fourth session. In this fourth session we are discussing about the Faraday's laws. In last session we are discussing about the galvanic cell in first session. In second session continuation part, what are the electrode potentials. In last session we are discussing about the types of cell and electrolytic cells, reference electrodes, all we have discussed. Now in this session we are discussing about the Faraday's laws. So in last session we have discussed the electrolysis. So in this electrolysis once again, so electrolytic cell we are taken. From one electrode, electrons are entered into the cell. Okay, so from one electrode, electrons are entered, and from another electrode, electrons are away from the cell. So this electrode is called as cathode, and this cell is known as anode, and this one is known as the electrolytic cell. Now by passing of current, then the substances are deposited at respective electrodes. Suppose if you take the electrolysis of sodium chloride, electrolysis of molten NaCl, that means sodium chloride is present without water. So what happened here, NaCl is splitted into, by passing of current, it is decomposed into Na plus Cl minus 1. Here the current is passed through the two electrodes, one is a cathode, another one is a anode. Cathode get the negative sign, anode get the positive sign. So negatively charged electrode attracts the oppositely charged ions. So what is the opposite charge for this? Sodium. Na plus is gain the electron, then form the sodium. So sodium is deposited at which electrode? Cathode. So at cathode, sodium is formed like this. Okay. At anode, what is the sign of the anode? Positive charge. So positive charge is attract the oppositely charged ion. What is the opposite charged ion? Cl minus. So this is converted to half Cl2 with liberation of an electron. So chlorine gas is produced at anode. So what happened? By passage of current, the sum of the elements are deposited at respective electrodes. So how much quantity of substance is deposited at electrode is given by the Faraday's laws. So what is the use of the Faraday law? How much quantity of substance is deposited at respective electrode, that one is given by the Faraday's laws. We have the two Faraday's laws, Faraday first law, Faraday second law. So first of all we are discussing about the first law. So by passing of current, sodium is deposited at electrode. How much is formed? That is the amount of substance or the amount of sodium is formed at respective electrode is directly proportional to quantity of current is passed in coulombs. That is a Faraday first law. So what is the statement? So the weight, amount of substance is formed. Amount is nothing but W. So amount of substance is deposited at respective electrodes is directly proportional to quantity of current is passed. Quantity of current is passed in coulombs. Okay. So according to this, W is directly proportional to Q. So based on this we get the one proportionality constant, that is the E. E means electrochemical equivalent into Q. This is the equation 1. E is nothing but which one? Electrochemical equivalent. Electrochemical equivalent. So what is the E value? E value is equals to equivalent weight of substance by 96,500 coulombs. Now here we get this one 96,500 coulombs. This is the value is equals to charge of 1 mole of electron. So charge of 1 mole of electron is known as the 1 Faraday. So 1 Faraday is nothing but charge of 1 mole of electron. What is the charge of 1 electron? See, Faraday represented with F, 1 Faraday is equals to 1 electron. Charge is 1.602 into 10 power minus 19 coulombs. In 1 mole, how many electrons are present? That is Avogadro number 6.023 into 10 power 23. By calculation of this, we get 96,483 coulombs. But for our convenience purpose, this value is written as 96,500 coulombs. So 1 Faraday is nothing but 96,500 coulombs, which is equals to 1 mole of electron charge. Suppose in a reaction 3 electrons are involved, means 3 Faraday of electrons are involved, or 3 Faraday of charge is involved. Suppose in a reaction 5 electrons are involved, means 5 Faradays. 10 electrons are involved, 10 Faradays. Now based on the previous slide, so equation 1 E is equals to W is equals to E into Q. From equation 1, W is equals to E into Q. This is the equation 1. But Q is nothing but current in coulombs. 1 coulomb is nothing but ampere second. Ampere is nothing but current. Current is nothing but represented with I. Second is represented with T. So this is the Q. This is the equation 2. From equation 1 and equation 2, 1 and 2. What is the equation we are getting? W is equals to E into I into T. Okay, I is nothing but current in terms of amperes, T is nothing but time in seconds, E is the electrochemical equivalent. Already we just know we have discussed, that is the equivalent weight by 96,500. So if you are pass the excess quantity of current, excess weight of compound is formed. If you are pass the less quantity of current, less quantity of substance is formed. So this is the Faraday first law. When it is applied, if only single electrolytic cell is given, then we are applying the Faraday first law. So Faraday first law is applicable for only single electrolytic cell. If only one electrolytic cell is given, then we use, then Faraday first law is applicable. Faraday first law is applicable. So this is the condition for Faraday first law. So what is the statement according to Faraday first law? The amount of substances deposited at electrodes is directly proportional to their quantity of current is passed. That means if excess of current is passed, excess weight of substance is deposited at respective electrode. Less quantity of current is passed, less weight of substance is formed at respective electrode. So according to this, we get this equation. This is the final equation 3. So when it is applicable, if only single electrolytic cell is given, then we are applying the Faraday first law. Now see the Faraday's second law. At which condition Faraday's second law is applicable? Second law. So what is the condition for applying of Faraday's second law? That is, if more than one electrolytic cell is given, if more than one electrolytic cell is given and both are connected in a series, then we are applying the which one? Faraday's second law. So if more than one electrolytic cell is given, more than one electrolytic cell is given, and connected in a series. Connected in a series. Then we can apply the second law. Second law is applicable. And one more thing, from each electrolytic cell we are passing the same quantity of current. So according to second law, suppose if you take the electrolytic cell, this is the first electrolytic cell and this is the second electrolytic cell, both are connected in a series. Suppose this is a zinc sulfate, this is a silver nitrate, and these are connected to the external circuit, and this electrode is the zinc and this electrode is the silver. Okay. Now what is the statement? When two electrolytic cells are given connected in a series, then from this if you pass the same quantity of current, if same quantity of current is passed, then the amount of substances are formed. Here which one is formed? Zinc is formed at respective of around the zinc electrode, around the silver electrode, silver is formed. Okay. So then the weight of substance is formed at electrodes is directly proportional to their equivalent weights. That is nothing but, what is the statement? Weight is directly proportional to their equivalent weight. So based on this, what is the equation we get? W1 by W2 is equals to E1 by E2. So this is the equation 4. This is the equation 5. In this before slide we use the equation 3. In this one we are using equation 4. So when it is Faraday first law is applicable, single electrolytic cell, but second law is applicable for more than one electrolytic cell is given and connected in a series and same quantity of current is passed from each electrolytic cell, then only second law is applicable. Here W is directly proportional to their equivalent weight. Faraday first law, weight is directly proportional to their quantity of current is passed. Okay. So based on Faraday first law and second law, from first law, what is the equation? W is directly proportional to I into T. There is a quantity of current is passed. From second law, W is directly proportional to their equivalent weight. So by solving of this, W is directly proportional to E into I into T. We get the one proportionality constant, that is W is equals to EIT by Faraday. But 1 Faraday is equals to 96,500. So by solving, and equivalent weight is equals to molecular weight by N factor. So W is equals to MIT by N into F. N is the number of electrons are involved. Suppose, let us take the example. See the question. 100 amperes of current is passed. For 10 seconds through sodium chloride. The weight of sodium is formed. How much weight of sodium is formed? How many electrolytic cells are given? Only one electrolytic cell. In that one, which one is present? Sodium chloride is present. If you are taken the sodium chloride, which one is formed? Sodium is formed. So what's the equation for this? W is directly proportional to Q, or W is equals to E into I into T. But what's the given data? How much amperes of current is passed? 100 amperes. So I value is equals to 100. And how much time is passed? 10 seconds. E means equivalent weight or electrochemical equivalent weight. What's the value? Equivalent weight by 96,500. What's the equivalent weight of sodium? Because of equivalent weight of sodium is equals to gram molecular weight 23 by 1. Because of sodium get the 1 charge. So what we get here? 23 by 96,500. Substitute this value. W is equals to 23 by 96,500 into I value 100 and time is 10 seconds. Two zeros get cancelled. 23 into 10, 230 by 965. So 0.25 around we are getting. Okay. So in this way we are solve the questions. So based on the given data, whether the given electrolytic cells are only single electrolytic cell or multi electrolytic cell. If one electrolytic cell is given, Faraday first law. Multi electrolytic cells are given, and second condition, connected in a series, and what is the third condition? Same quantity of current is passed or not. If all these are satisfied, then we are applying the second law of Faraday. Okay. So in this way we are applying the Faraday first law and second law. And see the next one. Here all this concept is dependent on conductivity. So conductivity or conductance is explained with respect to of resistance, capital R. Resistance is nothing but, here if you take a electrolytic cell, in electrolytic cell 2 electrodes we are used. These 2 electrodes are connected through the R, differed, the difference between R, these 2 are differed by the L distance, and from area of cross section is A. Then here it is a electrolytic cell connected in a external circuit. So in this one, resistance of the cell is directly proportional to distance between 2 electrodes. Distance is less, resistance is more because of same charged electrodes, or from this one current is passed. So that's why resistance is directly proportional to L. L is less, resistance is less. L is more, resistance is more. Now R is inversely proportional to area of cross section. So based on this, R is directly proportional to L by A. This is the equation 1. Okay. Now here L by A is also known as cell constant. Cell constant is nothing but the ratio between distance between 2 electrodes and area of cross section is known as the cell constant. Now what are the units for cell constant? For this, what are the units? That is, L is units are centimeter, area of cross section is centimeter square, we get centimeter inverse. So units of cell constant is centimeter inverse. Now go for the resistance. R is equals to some proportionality constant we are used, S into L by A. Here S is a proportionality constant. This is known as the specific resistance. S is known as the specific resistance, or this is also called as resistivity. represented with rho also. Okay, S is nothing but specific resistance or resistivity, both are represented either with S or rho. Now, suppose if L by A, that is nothing but cell constant is equals to 1 centimeter inverse, then what happened here? L by A value became 1, that implies R is equals to S. This is the definition of specific resistance. Okay, in a electrolytic cell, two electrodes are differed by the 1 centimeter distance and area of cross section is 1 centimeter square. Then resistance of the cell is also known as the specific resistance. Okay, so by using of resistance we can define the conductance. See the conductance. Conductance represented with C. So, the definition of conductance is, here conductance is nothing but reciprocal of resistance is known as the conductance. Okay. So, reciprocal is known as the conductance. From equation this is taken as 2. From equation 2, C is equals to what we can written as 1 by S into L by A. S is the constant, something by constant, or 1 by constant is equals to constant. So, what we get here, C is equals to 1 by S into 1 by L by A. S is a constant or resistivity, 1 by S is also constant. So, in place of 1 by S, we can use the K. K is nothing but kappa. Okay, instead of 1 by S, we can substitute the K. See here, C is equals to K into 1 by L by A. If L by A is equals to 1, in this, L by A is equals to 1, then C value is equals to K. Here K is nothing but conductivity. K is nothing but which one? Conductivity. Okay. So, see the units for the resistance and conductance. Suppose, see, units for R is ohms. What is the units for the resistance? Ohm. Whereas units for conductance is units of C, that is nothing but ohm inverse, or this is also called as mho. Okay, ohm inverse or mho. Okay, these are the units for the resistance and conductance. Now, here we get the one doubt. In this electrolytic cell, we use the electrolytic solution. The electrolytic solution concentration is either expressed in terms of molarity or normality. So, based on that one, we get the types of conductances. So, in this one, conductance is directly proportional to concentration. Remember this point. Concentration increases, number of ions are increases. Number of ions are increases, conductivity property also increases. So, concentration increases, then number of ions are increases, conductivity also increases. Okay. So, this is a conductance and concentration relation. Now, in electrolytic solution or in electrolytic cell, in this one, suppose one molar solution is used, concentration is 1 molar and the temperature is 298 kelvins, pressure is 1 atmospheric pressure. Okay. In electrolytic solution or in electrolytic cell, if 1 molar solution is taken, then the conductivity is known as the molar conductance. So molar conductance represented with mu. So what is the molar conductance? Concentration of the electrolytic solution is 1 molar, temperature is 298 kelvins, pressure is 1 atmospheric pressure. Then conductance is known as the molar conductance. So in this one, the conductance is known as the molar conductance. So see, in this one, molar conductance, what is the formula? That is mu is equals to K into 1000 by molarity. Okay, so that implies what we get here, mu into m is equals to K into 1000. This is the equation 5, this is the equation 6. Based on this, what is the relation? K is directly proportional to concentration. And what is the relation between mu and m? That is, mu is inversely proportional to concentration. That means concentration increases, molar conductance is decreases. Remember, but concentration increases, conductivity values are also increases, conductance is also increases, but except molar conductance and also equivalent conductance also. Instead of 1 molar, 1 normal solution is used. Instead of 1 molar solution, if you use the 1 normal solution, that is called as equivalent conductance. Represented with lambda. Okay. So equivalent conductance is, what is the equivalent conductance? Instead of 1 molar concentration, that is concentration is taken as 1 normal and the temperature is 298 kelvins, same atmospheric pressure. Then that conductance is known as the equivalent conductance. So lambda value is equals to K into 1000 by normality. So already equation 6 we are getting, this is the equation 7. By cross multiplication we get lambda into n is equals to K into 1000. So this is the equation 8. Okay. So based on this one also, lambda value is inversely proportional to concentration from equation 7. From equation 7 and 5, mu value and lambda values are inversely proportional to concentration. From equation 6 and 8, K value is directly proportional to concentration. So based on this one also, you may get the question in competitive exams. Okay. So this is the molar conductance and equivalent conductance. Now see the comparison between 6 and 8. From equation 6 and 8, what we get? Right side K into 1000, here also right side K into 1000. Based on this, what is the relation we are getting? Mu into m is equals to lambda into n. So this is the relation between molar conductance and equivalent conductances. Okay. Now see here, always conductance is measured in terms of equivalent conductance only. Mostly conductances are measured in terms of lambda values only. Here based on conductivity, here two type of electrolytes are there, that is a strong electrolyte and second one is a weak electrolyte. Strong electrolyte and weak electrolyte. Strong electrolyte is nothing but shows the more conductivity and easily dissociated at any concentration. Dissociated completely at any concentration, okay, at any concentration dissociated completely and shows the more conductance, shows more lambda value. But weak electrolytes are dissociated at low concentrations only. At low concentrations only it is dissociated, because of it is very difficult to dissociate. That is why it is called as the weak electrolyte. Now, in this one, here lambda value is dependent on which factors? That is, lambda value is directly proportional to strong electrolytes, inversely proportional for weak electrolyte. Okay, strong electrolytes are shows the more conductivity at any concentration, but weak electrolytes are shows the more conductivity at low concentrations. Okay, so lambda value is directly proportional to the, if charge increases, equivalent conductances are decreases. So inversely proportional to charge. Okay, inversely proportional to the charge. Charge is less, conductivity is more. And lambda value is more for strong electrolytes, less for weak electrolytes. Let us take the one example to understand this. Okay, so in this one, lambda versus concentration. Suppose if we are getting this type of lines, suppose this is the A, B, C. Here options 1, CH3COOH, option B or second option nickel sulfate, third one is suppose instead of this one CH3COONE I am taking, sorry, CH3COOH only, and third one KCl. Match these three. Okay, so based on this rule you have to apply, that is conductivity is more, lambda value is directly proportional to strong. So which is the strong out of all this? Your expectation is correct. This is a strong electrolyte, this is a weak electrolyte, this is a strong electrolyte. Lambda value is directly proportional to the strong electrolyte. So either third option or second option is belongs to A. Now which one is correct out of these two? Then apply the second rule. Lambda is inversely proportional to charge. So what is the charge of this one? Nickel plus 2, sulfate SO4 minus 2. Strong electrolyte K plus Cl minus. Where the charge is less? Charge is less, conductivity is more. So less charge is for which one? KCl. So that's why third one is matches with A. Second one is matches with B. Third one matches with, okay, A, B, C, okay. This is one, sorry. So okay. So in this way we get the clarity about this. Okay. Now equivalent conductances, suppose we are take the weak electrolyte. Weak electrolytes are shows the more conductivity at low concentration. At low concentrations only, more lambda value for weak electrolytes. For weak electrolytes, lambda value is more at low concentrations. So at very low concentrations, if lambda value is measured, that is called as lambda infinity, equivalent conductance at infinite dilution, because of Lambda value is measured at which condition? Very low concentration. At very low concentration it is measured, so that's why it is called as which one? Lambda infinity. Suppose if lambda value is measured at any concentration, lambda is measured, that is known as the lambda c. So lambda c, lambda infinity. Lambda c is nothing but lambda value is measured at any concentration. Lambda infinity is nothing but lambda value is measured at very low concentration. Now based on this one we get the degree of dissociation alpha, that is equals to the ratio of lambda c to the lambda infinity. This ratio is known as which one? Degree of dissociation. Degree of dissociation alpha is equals to lambda c by lambda infinity. So this is for weak electrolytes. But if you take the weak electrolytes, conductivity is more at infinite dilution. Infinite dilution conductivity is more, but the measured values are very low. So how we calculated? By using of Kohlraasch law, we are applying the, or we are calculate the equivalent conductance of weak electrolytes. So the Kohlraasch law we are going to discuss now. See, so what's the use of the Kohlraasch law? To measure the equivalent conductance of weak electrolyte at infinite dilution. So equivalent conductance of weak electrolytes at infinite dilution. Okay, equivalent conductance of weak electrolytes at infinite dilution is equals to sum of, sum means plus, sum of equivalent conductance of cation and equivalent conductance of anion at infinite dilution. This is called as Kohlraasch law. What is the Kohlraasch law? Equivalent conductance of weak electrolyte at infinite dilution is equals to sum of equivalent conductance of cation and equivalent conductance of anion at infinite dilution. That is known as the Kohlraasch law. So by using of, how we get? By using of strong electrolytes. By using of strong electrolytes, we can calculate or we can find the lambda infinity value of weak electrolytes. For weak electrolytes, equivalent conductances are measured by using of strong electrolytes. Okay, let us take the example. Suppose we want to calculate the equivalent conductance of acetic acid, lambda infinity of acetic acid. How we calculated? By using of which one? Strong electrolytes. See, equivalent conductance of at infinite dilution of sodium acetate. This is a strong electrolyte. Lambda infinity of HCl. It is also strong electrolyte. Lambda infinity of NaCl. By using of strong electrolytes, sodium acetate, HCl and sodium chloride. By using of these three, we are calculate the equivalent conductance of acetic acid at infinite dilution. See how you get this? That is equals to, first two are added, third one is subtracted. See why? Because lambda infinity of which ions we get? CH3COO minus plus lambda infinity of Na plus HCl is split into H plus and Cl minus. Lambda infinity of H plus lambda infinity of Cl minus NaCl, lambda infinity of Na plus lambda infinity of Cl minus. Now what happened here? Due to here sodium get the positive charge, but here it is a negative charge. Positive Cl minus, negative Cl minus get cancelled. So what are the leftover things? See, what are the things are left over here? Lambda infinity of CH3COO minus, here what is the leftover? Lambda infinity of H plus. By combining of these two, what we get? CH3COOH. Okay. So in this way we are getting this one. So equivalent conductance of weak electrolytes are calculated by using of strong electrolytes. Okay. So in this way we are identify the equivalent conductances of weak electrolytes by using of strong electrolytes, which is given by the Kohlrausch law. Okay. So if you are faced the any problem while solving the electrochemistry, comes to the nearest knowledge hub center, and this is the QR code. If you have any doubt to know about the courses we are offering, please scan it, then you get the total information. Okay. Thank you.